Welcome back to the Automation Podcast. Shawn Tierney here from Insights in Automation, and I want to thank you for tuning back in. This week on the show, I meet up with Lauton Rushford from Endress and Hauser to learn all about the latest innovations in Coriolis Flowmeters. And I also want to thank Endress and Hauser for sponsoring this episode so I could bring it to you completely ad-free. With that said, if you're interested in learning about what's the latest in technology used in Coriolis Flowmeters, I think you'll enjoy this episode. I know I did. And with that, let's go ahead and jump right into this week's show. I want to welcome to the show Lawton from Endress and Hauser. Lawton, it's great to have you on. This is the first time you're on the show. Of course, we've had your company on before. But Lawton, if you don't mind, could you, before we jump into Coriolis Flowmeters, which is an extremely important technology in our industry, could you first introduce yourself to our audience?
Yeah, absolutely. Thank you. My name is Lauton Rushford. I am the Flow Product Marketing Manager here at Endress and Hauser, based in Greenwood, Indiana, which is about 20 minutes south of Indianapolis, Indiana, at our national headquarters for Endress and Hauser. I've been with Endress and Hauser for 7 years now, a whole bunch of different roles, but for the last 3 years, I've been in this role, Flow Marketing Manager. Today, I really wanted to highlight a couple of awesome innovations that we've had in Coriolis Flow technology over the last, we'll say, about year or so, because I think there's a lot of use cases and a lot of awesome insights we can get from our Coriolis Flow meters. And yeah, so I guess we can kick it off. I did want to highlight Endress and Hauser as the manufacturer that I work for, and we have a long history of innovation. And so I'm going to kind of highlight that initially, talk about what sort of portfolio we have currently with our Coriolis flow meters, and then talk about a couple of new cool things that we have released over the last couple of months. And then finish off with what we call heartbeat technology. It's our advanced diagnostic system in all of our flow meters and all of our products across the board. It started with flow. So I think there's a lot of cool use cases, and I'll highlight a couple of those as well. And then, of course, Shawn, as the audience here, anytime there's questions or anything, please feel free to let me know, and I can try and address them as they come up. Okay.
Sounds good. Yeah.
Awesome. Great. So I guess our first Coriolis meter that we introduced into the market was back in 1986. So it's been some time. As you can tell by the slide here, there's a lot of different designs of Coriolis flow meters. There isn't one right way to do it, but I think that the way that Endress and Hauser has approached innovation is pretty awesome and pretty impressive. Everything from a single tube design to a dual tube design, dual straight tube design versus a dual bent tube design. There's a lot of different types of Coriolis meters out on the market. And we'll talk about a couple of differentiators that Endress and Hauser has on some products that we've recently released.
Just by looking at the slide here, the one that like really attracts my eye is the ProMass. That's the one that I think I've seen the most in the field.
Yep.
Walking around the different plants, and that was launched in 1998, so that's been out for
Yeah.
quite some time. So
Yep.
just wanted to throw that out there for those listening. That may be the one you've seen the most of in your travels.
Yeah, definitely. There's a lot of ProMasses out there. Our M-Point was the first one, but shortly after that, we released our ProMass, and we've just been, we've had a lot of iterations, which I think is also part of the impressive thing in terms of innovation that Endress and Hauser continues to do in terms of research and development on that. And the one that I always think about is the one that kind of looks like a UFO. That is our ProMass X. It's a high capacity, large diameter Coriolis meter with 4 tubes in there. So it's kind of bent 2 separate systems and then put together in one large device. And I always think that one's cool because it kind of looks like something out of Star Wars or something.
Yep.
So I think that's really, really cool. There's a lot of new things that we've released, and this is a short timeline of some of the innovations that we have, but over the last year or so, we've definitely invested a little bit more into specific applications, and that kind of leads us into our entire portfolio of Coriolis flow meters. We have 17 different sensors. So that is not a normal thing in the industry. I think that to some people, it can be confusing if you're looking at them all at the same time, a little overwhelming. But I think it's really important that I kind of talk about this in terms of every application that we look at. We're not trying to put one flow meter into that application. We're taking the application and the requirements of that application and designing a device that's meant for it. So in certain applications, you may not have to choose between 17 different sensors. You really have probably two or three that you're trying to decide between and weigh, both pressure drop, accuracy, density specifications, things like that will ultimately give you the best meter for that application. But we don't want to take an approach of trying to cram a sensor into an application. We would prefer to design the sensor in and meant for certain applications. So it does, I guess there's two questions on here. Why so many sensors? Well, because we want to design our sensors for specific applications. There's a lot of different applications out there. Doesn't that make it confusing? Well, of course it makes it a little confusing if you're looking at it from the high level 17 different sensors. But every application that we look at, we're trying to there's a lot of different requirements of applications in oil and gas versus life sciences, and we wanted to design sensors that fit the market and fit the application that they're supposed to go into. And in general, all of them work the exact same way. As a general rule of thumb, your Coriolis Flowmeter measurements are mass flow, density, and temperature as a starting point. We'll talk about a couple of features that we've started adding to some of our flow meters that create more of a multivariable device. Instead of just measuring those three things, we can add viscosity, or we can do other things, or concentration, things like that with the meters. But in general, the mass flow is using the phase shift between your inlet and outlet pickup coils, and taking that into account to relate it directly to the amount of mass that's within those tubes. And then similarly, as the tubes are oscillating, a more dense fluid is going to have a lower resonant frequency. And based around resonant frequencies, we can understand how dense the fluid is inside of those flow tubes. And then we also have on every single one of our Coriolis flow meters, P247 temperature probe that's attached directly to the inside of the outside of the tube within the secondary containment for additional values, additional multivariable uses. I mean, for example, on a concentration measurement, really what you're using is density and temperature in conjunction to relate that to a concentration. So that's something that would add to the use cases for a Coriolis flow meter. And one of the current biggest innovations that we've had recently is with our ProMass Q. The ProMass Q is a little bit of a different design than some of the other ProMasses that you may have seen on some previous slides. We actually have a little bit longer tube that's has a more harsher bend in it. The reason for that is because what we're trying to do is we're trying to oscillate these two sensors, or these two flow tubes at the same frequency, but in two different modes. So in multiple frequencies at the same time. So essentially what we're doing is our historic use of a ProMass meter is kind of in that top visual where we're oscillating in one frequency. And one specific frequency depending on the fluid that's going through it. And then at the bottom, we show an additional mode of oscillation. So an additional frequency that we're oscillating at that gives us additional information for specifically challenging applications. So in a lot of these cases, what we see in most of these applications is a lot of whipped products, purposeful entrainment of air into applications. So cement in general, let's say, as an example, we can start there. Well cement, it's aerated all the time. So as you are are moving that cement around. Air pockets can be filled inside of that cement and can cause challenges, as most things with air cause challenges, especially as you're moving into a multi-phase fluid. Anytime you have one or more than one fluid phase within the meter, the meter can is it's almost like the meter's kind of confused. It's not really sure what it's supposed to be reading and what it is reading and why it's reading that. So with multi-frequency technology, we can actually internally compensate, because we're oscillating in two modes. We can compensate for the air that's present and give a corrected mass flow and a corrected density. So a lot of milk applications, cream cheese, well cement, anything like that.
That's awesome. Could you back up one slide for a second?
Sure.
I find this so interesting, but I know that the audience, not everybody's on the same page.
Right.
So I think this would be a great slide. Could you just like what the basic operation of a Coriolis Flowmeter is? Okay. We know we're trying to measure typically the flow, right? The flow rate, right?
Yep.
And there's all these variables that go into it, but could you really just give us the introductory, how does this thing work?
Sure. So there are exciters, if you will, or vibrating electronics that's going to oscillate those flow tubes.
Okay.
And they're going to, if there's no flow in it, the oscillation is going to basically be very in line, in sync. Your tubes are going to move out and then move in. And again, these are a little exaggerated in terms of videos, but the actual tubes will start vibrating, almost like a tuning fork, or you hit a wine glass on the side of a table and you get the vibration out of the wine glass. That's kind of the same vibration that's happening. And now as we start flowing product through those flow tubes, we get these waves that are created. And the inlet and outlet pickup coil are now not in sync, meaning that we're using the Coriolis force, or we're essentially looking at a phase shift as those tubes start to create those waves. Where there's a time difference between the inlet and the outlet pickup coil. And that time difference is ultimately what's related to phase shift, which is ultimately what's related to that mass flow that's inside the tubes. Similarly, as we're oscillating those tubes, if we have water going through those tubes, well, we know what the resonant frequency should be of water. We also know what the resonant frequency is of a more dense or a lighter, less dense fluid. So now we can start understanding what the density is specifically as well. So that's where kind of the multivariable measurements happen within the flow tube. But essentially, all of it's based around a time measurement. It's all based around when does this pickup coil pick up this tube, and when does this outlet pickup coil pick up the tube coming back. Yep.
Yeah, and so we talked about the ProMass Q having two modes, because when the liquids, or like the substance like cement or dairy, cream and whatnot, have a lot of air in it, that could be a challenge. So you have this other mode. We also talked about having the temperature sensor thermocouple built in. Is temperature always, and I know I'm asking a lot of crazy questions here, but is temperature always a factor? Because I can see definitely products operate very differently based on the temperature. Is temperature always a factor and comes up with the calculation?
So typically, temperature is going to affect not only the fluid, it's also going to affect the properties of the tubes themselves. So that's something that's often overlooked. And when we're looking at applications, yes, we care about what the temperature of the fluid is, because the density of that fluid may change. There may be more or less mass flow depending on how close a pump is. There's a lot of installation effects as well. But ultimately, as those tubes are oscillating, if the temperature is low enough or the temperature is high enough, those tubes have the potential to move more or less as you're oscillating them. So that's where temperature plays a really big factor, not only in measuring temperature, that's a great added value, but also in the thermal properties of the actual tubes material themselves.
Thank you for taking my questions. I just find this interesting.
Yeah. Oh, that's great. That's a great question. That is something that isn't really thought about, but we always have to take that into account, and that's part of ensuring that the stated accuracy, the specifications of the device are met throughout the entire temperature range of the meter's specification. So if we know that we're going to be operating, this meter is rated for -40 degrees F to 300 degrees F, well, we have to make sure that we understand how the tubes will react throughout that entire range. And that again goes back to that innovation, that goes back to the research and development that goes into the design of these sensors. So a lot of important things there. So with that, I guess there's another added value that comes into play when we talk about oscillating that ProMass Q at two modes. There's actually an additional effect that happens to the tubes. And as those tubes, because of how long those tubes are, as the tubes start oscillating, at the end of their oscillation, at their maximum amplitude of oscillation, you get a slight twisting motion in the tubes themselves. And so we have a device that is called our ProMass I that directly measures viscosity directly out of the meter. And that is using a similar technology in a torsional oscillation mode, whereas the ProMass Q, just by nature of design, actually has some slight twisting motions. So, our R&D experts and geniuses overseas, they came up with this idea. Well, why couldn't we do a similar thing with our ProMass Q? Why couldn't we look at how much shear we're placing on the fluid or how much twisting we're placing on the fluid and understand maybe a little bit more about the individual properties of that fluid that's going through the meter? And that's where the oscillation, the torsional oscillation or the rotational oscillation of that flow tube can give us a little bit more insight into the viscosity of the fluid itself. And so this is where kind of another innovation, which is on the ProMass Q, the hydrocarbon viscosity monitoring. We do what's called, we stated it's for hydrocarbon viscosity. And the reason for that is because hydrocarbons have a very known viscosity profile across all different pressures and temperatures. And so we can verify on water and ensure that the meter is going to react properly and maintain the accuracy that we state it's going to have. And again, this is a monitoring point. It's not necessarily a calibrated point. It is plus or minus 10% accuracy, which isn't very high, but it's enough to where you can start seeing when you have the difference between a very heavy crude oil and water, or a very light crude oil or a light hydrocarbon. And the repeatability is ultimately where the use case comes in. So this is one of the highlights that I wanted to point out, because I think not only on the monitoring side, it gives us more values, it gives us more information on what's happening inside the meter without us having to open up the meter or open up the pipe and look at it. So a couple of applications, typically you're going to see them both in all parts of oil and gas, which is upstream, midstream, and downstream, all the way into refining products. A lot of these applications in midstream, especially in pipelines, is going to be the addition of some sort of drag reducing agent. So we can understand as we start adding that drag reducing agent into pipelines, how much effect is it actually having? Are we changing the properties enough of the product, or is it? Are we not changing it? Are we changing it too much? It gives us more of a qualitative understanding of the product that's going through the meter. So, and I'd mentioned earlier, we do a lot of industries, but I guess the two completely opposite industries would be something like oil and gas and life sciences or pharmaceutical. And that kind of plays into this transition here into our ProMass U. This is our is a relatively new product that we've had out for less than a year at this point. But our ProMass U is our single-use Coriolis technology. In a lot of pharmaceutical applications, there's a lot of challenges in terms of cleaning, in terms of making sure that there's no risk of cross-contamination. And the biggest thing with that is the introduction of single-use production. So taking cells, biology, all the way through to a marketed medicine or a product, but using all single-use products. And that saves on risk for cross-contamination, especially in large factories. And it also actually does save some money because of the amount of chemicals and cleaning that has to go on in a lot of these pharmaceutical companies. A single-use technology kind of fits the need in that industry very, very well.
So what I'm looking at here is it looks like a lab tabletop type device,
Yep.
and the U, right, the pipes is replaceable. So
Yes.
it looks like a cartridge where you would turn a lever. You could, let's say you ran product one, and you ran that for a while, and then you're done. You turn this lever, release the cartridge, pull it out, and those pipes don't have to be cleaned. They can
Right.
be disposed of. And now you can put in your new one and you can run a different product. And we all know, like a few years ago, we all heard the horror stories of a pharmaceutical that mixed two different batches of medicine, and it was like nightmarish. Thank God that never got out into the real world, because only God knows what would happen. So you can't we can't that type of cross contamination just can't happen in
And
the 21st century. So, but this is so interesting. Is this something that would be in a? I'm just looking at such a nice looking desktop device. Would
yeah.
this be something that was only used in a lab, or could it actually be used in a production line?
Yeah, so there's two versions.
Okay.
There is a tabletop, which is what you can kind of see on the screen, where we have
Okay.
this chassis built around there's really three components in this. There's a transmitter that's kind of sitting at the top there. There is a base unit, which is where the sensor goes into, that has all the electronics. And then you have your disposable sensor. So the
Okay.
sensor is where all your fluid is going to be flowing through.
Mhm.
The base unit is doing all of the manipulation on the tubes themselves. So we talked
Okay.
about how a Coriolis meter works, or oscillating those tubes. The base unit is actually doing that. And then the transmitter is taking all of that raw data, understanding it all jumbled up, and giving it out a flow rate, a very accurate flow rate. And there's two different versions of this. There is a desktop version and a panel mount version. So the panel mount version would be, in a skid of some sort.
Mhm.
That would be permanent, but then the single use cartridge would be pulled out, disposed of, and then a new one would be replaced there. And that's kind of what we're going to get to in a little bit once we start seeing some of the challenges in this industry. So this industry really is it's not new, but it is in terms of process instrumentation. There's not a lot of manufacturers out there who have single-use flow technologies. So there's a challenge from our perspective as the manufacturer to try and meet all of the requirements of the industry, while providing a robust, accurate, reliable sensor for these applications. And so that's where our R&D kind of hit a snag at one point, almost, because they're so used to making robust products that last
Mhm.
10, 20, 30 years in process. Now we have to look at a product that we want to also do all of those things, but also be disposed of. And so there's some challenges there. Similarly, there's a challenge of calibration in a lot of pharmaceutical plants, because certain products require calibration before they're even installed. Certain products require calibration before they're installed and while on site. And then if there's ever a replacement that goes in, there's an additional calibration that might have to happen. And so what we wanted to do was take all of those constraints, all of those challenges, and try and check the boxes of all of them. And I think that's kind of where our single use landed. There are still some certain applications that are a challenge, but they're always going to be a challenge until there's some innovation that comes out that truly meets that need. But I guess in general, really, if you look at a high level, it's a 0.5% accurate device. We have 4 different sizes of sensors that can go into the same base unit. We have an 1/8 inch, a 1/4 inch, a 1/2 inch, and a 1 inch sensor that will go into this base unit. They all fit into the same base unit. So as we talked about it with an example, using product A, maybe you're only flowing at 10 liters per minute, but then product B, you're flowing at 75 liters per minute. Well, technically, those should probably be 2 different flow meters, but we can just change the different cartridges out, and there's no risk of contamination, and there's no need to change anything other than the sensor itself. It is gamma sterilizable, especially in pharmaceutical. That's really important to make sure that there's no contamination at all from anything in production, from anybody's hands getting on it or anything like that. We don't do it as a manufacturer. We would kind of rely on our OEMs, on our tube set manufacturers to actually put these skids together, and part of that package would be to gamma sterilize all of the fittings, all of the tubing, as well as the flow sensors. And then we also talked about the different designs that we have. It is stainless steel tubes, which is different, and it's polycarbonate flow splitter. So if you see that purple part on the screen, where our tubing would come into, that is a plastic or a polycarbonate product. And then the tubes themselves, where we're actually performing the measurements, is a stainless steel 316L material, which is different because when you think about single use, you think about plastic, you think about bags that are plastic, bioreactors that are plastic, because they're easy to throw away and they're inexpensive. But we felt like in order to meet all of those challenges and all of those constraints in terms of current sensor designs, we felt like the most robust way to do that would be to use stainless steel. And we have a long history of manufacturing stainless steel devices. And so this is just another way that we could show our expertise in products and especially in Coriolis meters. So there are, as I mentioned, 3 components. You have your base unit or your single use disposable sensor down at the bottom there. You have your base unit, which is again where all your electronics are, and then you have your transmitter. And there's a cable going from the transmitter to the base unit. There's a couple of things I want to highlight on the inside of what the meter is and what it looks like. The first thing, probably the most important, is that barcode scanner. So every single one of these disposable flow tubes gets calibrated at our factory and then gets imprinted a QR code on the inside of the flow meter. And that QR code, that 2D barcode scanner, actually scans that information. So it can accurately pull in the calibration information. It can pull in the serial number of the tubes. It can pull in the line size of the tubes. It can pull in a lot of information related to those tubes. And then it can relay that back to the transmitter, and the transmitter can check to make sure everything seems functional. And that kind of falls into where our heartbeat technology conversation may come in just a little bit. And then again, all the electronics, so our sensor electronics boards, our ISEM or our sensor electronics module, all is based inside that base unit. Inside this very large, not very large, but a very heavy bodied base unit to ensure stability across the board. And so here's an example of what that QR code kind of looks like on the back side of that flow tube, and then another look into kind of what the inside of the base unit looks like. you see coil inlet 1, coil inlet 2, or coil outlet 2. Similarly to kind of what we talked about before, we really care about what's going on in between those tubes, in between those two coils. And so we're magnetically oscillating the Coriolis flow tubes inside at that back piece, that back what is that? It's like a gray type ceramic piece in the back, and that's ultimately giving us that oscillation that we're looking for. And then our inlet and outlet pickup coils are also magnetically coupled to the sensors, and we can detect very small changes in those those oscillations. So very, very cool, very innovative. It's a product that we've had out for a while, and less than a year, but long enough. And there's been a lot of interest in the pharmaceutical space, especially as people are trying to save costs, go closer to maybe a personalized medicine approach, where there's going to be smaller amounts of product going through, more expensive amount of product going through. Accuracy is going to be the most important there. And so this is where we kind of talk about a little bit more about how to maintain that data trail, that automated data trail from the calibration in the factory all the way into production. And so in this case, what we're looking at is, here's the process of what would happen in a system. We would calibrate the tubes at our factory. The tubes would go to a tube set manufacturer. The tube set manufacturer puts all of these pieces together. They double bag them in a Class 7 ISO Class 7 environment, super clean area, no risk of contamination there. And then just to be even more safe, they're going to gamma sterilize it there. And then they're going to bring it on site where they have their skid created, and they're going to plug everything in. And then once they plug everything in and turn the entire skid on, they're gonna notice that on the flow meter it says, hey, we're doing a function check right now. Well, what does that mean? That's ultimately what we call heartbeat technology, and that's doing some advanced diagnostics behind the scenes, and it's checking information like electronics in the base unit. It's checking tubes, making sure the tubes are aligned and weren't damaged in shipping, and ensuring that the factory calibration is still valid on the current device. So all of that is happening kind of behind the scenes before you even start running product through it, to ensure that we are fully CGMP or current good manufacturing practice and operation on a production side. And that kind of maybe leads a little bit into another product that we've recently released, which is our Endress and Hauser ProMass K10. It's the first Coriolis meter in the world that has IO link as an output. And now IO link, I think it's really important to start with a really good basis about what IO link is. And IO link is something, I call it the 3-wire digital communication, but it's not 100% accurate. So we'll maybe dive into that a little bit and talk about what IO link can do, and how it is being accepted in industries, specifically in in food and beverage and pharmaceutical industries. As a general rule of thumb, most large smart factories are using Ethernet-based protocols. So that means that the devices that they have, the control system that they have is all digital, which means you can get a lot more data. You can get a lot of data. You can get so much data you have no idea what to do with. There's also these Ethernet switches that are typically either remote Ethernet switches or switches that are out in the plant that are pulling in a lot of this data and then sending it up to whether it's their asset management system or a control system, and ultimately can give us the most amount of information about the health of the device, any sort of multivariable values that we have coming out of the device. And then similarly, on the right side here of this screen, you see an IO link system. IO link also does a very similar thing where you have a remote, what's called an IO link master. It's connected to a flow meter. or connected to a level switch or connected to a temperature probe, and it pulls all of that information in, and then it outputs that information back to their control system. And so historically, we've had a lot of Ethernet 4-wire devices, whether that's Ethernet IP, Profinet, Modbus, any sort of digital HART as an option as well. That's historically been where our Ethernet 4-wire and 2-wire devices come from. Now, IO-Link hasn't really been a focus for us, but because of our diversity in different industries, we've had to look at IO-Link as a feasible, cost-efficient choice for basic process needs in flow meters, in pressure transmitters, in a lot of devices, and a lot of different applications. And so there's some benefits and pros and cons to both. Ethernet, you have a lot of process devices versus simple measurement points. The IO-Link, you have a specific range in terms of distances. That's only about 60 feet, which means it's really, really good for those skid solutions that are put out into many, many factories, and especially in food and beverage. These IO-Link masters are really where the integration happens. And then the data that's recorded and aggregated is happening inside that IO-Link master, where typically on a Ethernet-based system, you will have full transparency from device level all the way up to your control system, DCS system, throughout and anywhere throughout that system as well. There is uses for both, even in the same plants. There's uses for both in similar applications. But I think one of the benefits is being the first Coriolis manufacturer to have an IO-Link device. What does that mean? Really, what it means is we can get some very good data, not all the data, but in many cases, we don't need all of the data. And we can be super accurate, extremely fast in terms of data transmission, and make things a little easier in terms of integration and installation of the devices. So typically what a system or a subsystem might look like with IO-Link, you have your IO-Link master. That's where power is brought to. And it's also where our connection to that overarching enterprise system or DCS system is. So that IO-Link master is a must. You have to have that. You also have to have a flow meter or any device that is capable of outputting in an IO-Link protocol, in an IO-Link communication method. And then there's a specific 3-wire cable that goes from the device to the master. And this is the often overlooked thing, but it's an IODD. Essentially what that means is it's an IO-Link device driver. So that device driver is going to tell the IO-Link master what and how is this device sending information to me. So it's almost like a little roadmap for the IO-Link master to understand what's happening on the base level of that IO-Link device. Ultimately, these are the 4 things that you have to have for basic subsystem components. And then as you start integrating it into an overarching system, there's a little bit more that would be needed as well. But this will at least get you started in understanding kind of why there's IO-Link masters and why there's IO-Link protocols and technology in the first place. So again, this is our Coriolis K10 with our IO-Link master. It's a line size 3/8 of an inch all the way up to 3 inch. It also has what we call heartbeat technology. It has 3A. It has all of our approvals for hygienic applications, for food and beverage applications, for pharmaceutical applications as well, and gives us a little bit more flexibility in terms of what we can offer our customers that will meet the need of where they're at, but also prepare them for future expansions and large scale DCS turnarounds and things like that. So there is a couple of things here: mass flow as a standard with density, temperature, and you get a standard totalizer 1 as an output. There is, again, food contact materials, E-Hedge 3A, all hygienic process connections, as well as standard process connections available with this device. And then one other key factor here is when we're actually interacting with this device, there's a couple of ways we can interact with it. We can, of course, use a touch screen. We can push the device and be right in front of it. There's also a method for using a free app that we have on the Android store and the Apple store. That's called Smart Blue. That's available for a lot of different devices, but it is using a Bluetooth technology to tap into the device and configure everything. And then the other option is using a device manager with a CDI port that's built inside the transmitter as well. So all different ways to interact with the same device, even interacting with it using IO Link is possible as well. So a lot of different functionalities, a lot of different options, so we can meet the needs meet the customers where their needs are, and then also where they want to get to. So that kind of takes us into what heartbeat technology is. And we talk about heartbeat technology as a story, because I think if we start talking about what it is before we talk about the story, it's hard to wrap your head around. There's a lot going into it. And part of that discussion really starts with a marketing phrase, which is called taking the pulse of your measurement. And what that really does is it's trying to understand how the device is operating currently and how the device may be operating in the future based on current conditions. And so all of that is started with what our customers expect out of a flow meter, expect out of a pressure transmitter, expect out of a pH probe. All of our customers' needs and our users' needs are expanding. So not only do they need excellent measurement performance from a device, they also need a reliable device. I need to know when something's going wrong. They also want to be available. If the device itself isn't always available, they can't trust it. We want our customers to not only trust our device, but trust the measurement performance that they're getting out of the device. And they also want it easy to use. As we've seen in a lot of industries, the operations teams, the operators that are on the plant floor are getting less and less. And maybe they're moving more towards engineering. But there are a lot of plants that are running extremely lean. And so running lean means they have to run efficiently and they have to run effectively. And if our devices are not easy to use and easy to understand, we're kind of failing at that point. So we also want to make sure our devices are safe. We want to make sure our devices are predictive. And we want to make sure our devices potentially can be connected in the future. And so all of those together is now we've got a difficult puzzle we've got to try and solve with any one of our measurement devices. And that's where we think kind of heartbeat technology meets a lot of those needs and bridges the gap between the excellent measurement performance and all of these needs that we have. So we split heartbeat technology into kind of three categories. We have diagnostics, which is current status, current device diagnostics, advanced diagnostics. That's the basis of everything. So if we don't have a good basis of diagnostics, we can't do verification. We can't do monitoring. We can't provide improved process insights very effectively if we don't have a good base unit. So that happens from the design of our devices all the way down to the raw components that go into all of the devices as well. And then verification is kind of what's happening to my device right now, and can you give me a PDF printout of what that looks like? So that's part of the verification. And then again, monitoring how we look at certain values over time, trended over time, so we can start understanding predictively when certain process conditions or process upsets may happen or could happen, and how will they affect our measurements. So all of that together is really bridged on the diagnostic coverage. It's based around how we can detect our any alarms, alerts, failures, things that happen inside the device that weren't expected. All of that needs to be really, really important. And so our I/O modules, our sensor electronic modules, our sensor inlet and outlet pickup coils, and the entire excitation system that's happening inside of a Coriolis meter, all are really, really important to understand the health of the device. If we can understand the health of individual components of the device, we can try and better understand the health of the entire device as a whole. Kind of the sum of equal parts, or the sum of parts is greater than the sum of the system. So that's ultimately what we're trying to do here. And what that means is that this value, the heartbeat sensor integrity parameter, is always generated and can be used as a direct value for understanding process-related concerns as well as meter concerns. So in a similar way, we talked about oscillation modes with our ProMass Q, with our ProMass I, and other flow meters as well. The frequency, or the oscillation frequency, that we're actually doing for this HPSI value is a fixed distance from that frequency. And so at any one time, we're oscillating these tubes at 1, 2, almost 3 different frequencies every time. And so the part of this parameter is ultimately giving us a little bit more information related to the health of the sensors, related to even the health of the process as well. And we'll talk about a couple of use cases on how that and what that means and can ultimately mean for you. So as a general rule of thumb, when we calibrate and design a new sensor, our HPSI value is 0% at reference conditions, and that may fluctuate depending on if you're operating at reference conditions or not. But right around 0, it could be negative 0.1 to positive 0.1%, but there's no cause for concern there. We do have kind of a stated bandwidth in which we expect the flow meter to operate well within its factory calibration and well within its specification. But if that value shows very, very low or values like right around 0 as a reference condition, your HPSI value is related directly to sensor components that aren't affected. So if our exciter current, if our pickup coils, if our sensor tubes are not damaged, likely that HPSI value is going to remain at 0 or right around 0. Now, when we do have something like a wear mechanism, something like corrosion or erosion or abrasion inside the tubes, ultimately there's things that are going to be affected by that. Now, how do we actually detect that? Well, that's where, using this HPSI value, we can actually understand individual components of the flow meter, individual components like the sensor tubes. For example, if we were to have a corrosion instance, your wall thickness of the tubes would change. And so what would happen there is, as we start oscillating these tubes, you would start to see that value increase because your tubes are moving more and more and more, because we're oscillating at the same frequency, or at the same frequency, but our tubes are not as heavy, right? So that's where that HPSI value can give us information related to kind of the health of all of our devices, or all of our components within the device. So there's multiple ways to observe that HPSI value, and this is where trending comes into play. Looking at something and trying to be predictive and preventative in the long term. There's no process interruption. This entire thing happens. This entire HPSI value is generated automatically by the device itself. The measurement remains completely available, continuously available, and it happens in situ, behind the scenes, if you will, of your measurement. And then you're going to improve efficiency, obviously, and reduce risk if you understand what's happening and what's going on inside the flow meter without you actually visually seeing what's happening to the device. So all of that to say, there's a lot of ways to observe it, but there is also important ways that we can use it. So Yes, knowing that the HPSI value is 0 is that's great. That's awesome. But what does that ultimately mean? And here's a couple of examples. Here's a couple of use cases. So we've had an application in the past where it was an abrasive fine slurry. And so anytime you have abrasive fine slurries, you have to be extra cautious of using bent tubes, um, and also the velocities in which you're flowing those processes through there. So the initial one they had was a dual bent tube that failed 6 months into service, and they replaced it with a single straight tube. So they expected to see some abrasion, but because of the design of the flow meter, that HBSI parameter was taken over time, and it's been installed for 4 years now and shows a relatively flatline behavior for the HBSI value, meaning there's no wear mechanism going on inside that device because of the process. So that's a use case there. Another use case that we talk about a lot is the presence of abrasion in general. We know that in some applications there is going to be abrasion, and that's on us as the manufacturer. That's also on the customer to understand what their levels and limits are and are capable of handling. And if they don't know, that's where we should probably step back and say, hey, let's talk about this at a high level. What happens when something goes wrong? Do you just automatically remove the device? Are you down in terms of not being able to produce properly? Things like that. And that's where, in this case, we used kind of predictive maintenance. Every 10, 12, 15, 18 months, we know we have to replace this device because of the abrasion, or we have to decrease our velocity through the meter. So either way, that's ultimately this use case and showing that there is a wear mechanism happening, and we need to understand at what point do we need to start replacing these devices. And lastly, here's one that was an unexpected wear mechanism. So customer used a Coriolis Flowmeter, and for 5 days, everything was great. No worries. Everything was totally fine. Customer didn't expect anything to be wrong, which is exactly what was shown. And then once they did a cleaning cycle with a new cleaning product, they noticed that this value increased. And so over time, I mean, think about 25 days, you're increasing your HBSI value because you're performing your regular scheduled cleaning. Well, that wasn't understood, and that wasn't the customer didn't know that was going to affect things. We didn't know that was going to affect things, but this ultimately shined light on here's what's happening. Now, can we change cleaners, or can we use a material that's more compatible with that cleaner, or can we just live with the risk that the values will last long enough for us to get really, really good data, and then we can and look at replacing it, things like that. So this was another application where we weren't expecting to see any sort of drift, but we did because of the wear mechanism that wasn't very well known or present at the time. So ultimately, I think using something like heartbeat technology as a confidence booster in your measurement is really the key there, because I think the more that we can increase confidence in our measurements, the more that our customers will continue to want to work with us and collaborate with us on applications and talk about different industry applications and things like that. As the working for a manufacturer is currently my first job, I think out of college, I think there's a really cool benefit of a privately owned company that continues to invest in research and development for the products that we have. And I think that Endress and Hauser has done a great job of showing some innovations that we can within our Coriolis Flowmeter technologies. That's all I got.
Well, I thought that was very interesting, especially the HBSI, how you guys have included that in your product so you can see that everything's good, or if something is starting to go out of I don't want to say out of whack, something's starting to go out of alignment, with
Yeah.
what you were expecting. And that example of the cleaning Nobody would have thought, this product is designed to run this fluid through it, but the cleaner, finding out that the cleaner was the problem, that's
Mhm.
priceless, right? That's
Yep.
priceless. And like you said, there's different options you can take to address that issue. But now that you know what the problem is, if you didn't know there was a problem, then your values would be off over time, and that wouldn't be good at all.
Right.
So it's just such an interesting topic to talk through. And I appreciate you not only taking us through your products, but also taking us through some of the technologies that are built into products and that make them work. And there's a lot there between the field bus, the Profinet, and the Ethernet IP on your really high end, high accuracy, type of installations versus on maybe a smaller installation where you can use IO Link because it's lower cost. We just had the IO Link folks on the podcast. If you guys missed that, just check back a podcast or two ago. We had the IO Link guys on talking about what they do and how they do it. And I think you summarized it very well in this presentation. And so I think that makes a lot of people happy because in many cases, that's a lower cost. Yeah, I mean, you're not going to get the same performance as you're going to get over Ethernet, but it's a lower cost and it's might be enough information for your application. So it's good to see that option there, especially for those skid manufacturers who can utilize those products. With that, I don't have any other questions. Was there anything else you wanted to say before we close out the show?
No, all I have to say is thank you. I appreciate the time and the platform. I think this is awesome, and thank you for asking all the questions you did. I think there was a lot of really good information that you mentioned as well there too. So, uh, thank you. That's all I have to say.
Well, Lawton, thank you for coming on. I just like the first time we had Endress and Hauser on. It was just really just so intellectually interesting. So it's our pleasure to have you on, and we really appreciate you guys.
Thank you. Appreciate it.
Well, I hope you enjoyed that episode, and I want to thank Lawton for coming on the show, not only to bring us up to speed on Coriolis flow meters, but also answering my questions, because I know I interrupted there, especially at the beginning with a lot of questions. So really appreciate him taking my questions and also bringing us up to speed on the technology. Now, I also want to thank E&H for sponsoring this episode so I could bring it to you ad-free on all platforms. I don't like ads, but you got to pay the bills. And when a vendor comes in and they sponsor the show, it really underwrites our cost to edit it and publish it. So I'm super appreciative to them and to all our sponsors who do that. And please let them know if you see E&H anywhere out there, if you're talking to one of their reps or you're talking to somebody from E&H, please let them know how much I appreciate and maybe you appreciate that they sponsored this episode. I also want to mention that, and you may not know this, but I brought my other podcast back, the Automation News Podcast. I renamed it Automation Tech Talk. And anytime I have an episode that is one of my shorter episodes that I think will do good on audio, be a good listen, right? I am publishing it on that Automation Tech Talk podcast. And on this podcast, you probably notice every once in a while I'm releasing an episode of The Automation Show. Some episodes of The Automation Show, there's so much hands-on that I don't think they'd make a good audio edition, but some of them are like presentations and discussions, and I think those would make a good episode of the Automation Podcast, so I'm releasing them on this podcast channel, but I'm keeping the name The Automation Show, so hey, this is originally was a video that was turned into a podcast. So give me feedback. If you don't like those, I'll stop doing it, but I thought because some weeks we can't always bring you a new episode. We may have an episode of the Automation Show that I think would make a good listen. So I wanted to bring those to you on this platform as well. And again, I always love your feedback. And I want to thank everybody who's given us 5 stars or thumbs up. You guys are great. Last time I checked on it, so many people had given us 5 stars. And, that's really how we find new vendors come on, like E&H and other vendors, right? They specifically said you guys had such great feedback on the previous podcast that they wanted to come back on. So please take a moment. I know a lot of you listen while you're driving, but when you get home or get to some place where you can look at your phone, please give us a thumbs up or a 5-star rating, because that really helps us grow the audience and find new vendors to come on the show. And with that, I'm going to end the show right there. I want to wish you all good health and happiness. And until next time, my friends, peace.